the different processes that we have been reviewing, the first step was glycolysis. And when we put in 1 molecule of glucose, we got out 2 molecules of pyruvate. We profited 2 ATPs and 2 NADHs. The second step was intermediate step, and we started off with 2 pyruvates and ended up with 2 acetyl-CoAs. We lost 2 molecules of CO2, and we made 2 NADHs. And then the Krebs cycle, we started with 2 acetyl-CoAs, and we lost 2 molecules of CO2. We made 2 ATPs by substrate level phosphorylation. We made 6 NADHs and 2 FADHs. But in this whole scheme of things, we are still nowhere near 36 to 38 ATPs. If I count them up, there's 2, 4 ATPs. We have a lot of NADHs and 2 FADH2s, but not a whole lot of ATPs. So here was the subtotal. 4 ATPs. If I count them up, remember I never went back and doubled up our numbers over there, but if we doubled them up, there was 2, 4, 6 NADHs just over in the Krebs cycle. So if I add them up, that was 10. And then FADH2, we had 2. And then remember when we cash them out in ETC, NADH would drive 3 of the proton pumps, so we'll get approximately 3 ATPs. So there's where we get a lot of our ATPs, 30 ATPs with our electron carriers, NADH. And then we bypass one of the proton pumps with FADH2, so we just multiply by 2, that gives us 4. So if we add them all up, that's 30 plus 4, 34, and 4, 38 ATPs. Now this is where you get that discrepancy. Remember I said some folks will say 36, some will say 38, because there is a fee over here. So it's kind of like being in Illinois. There's a toll here. And for every molecule of pyruvate, there is a toll of 1 ATP. So we actually use 2 ATPs because we have 2 molecules of pyruvate, which is where you get that 36 number from. So we've talked about active transport earlier this year and how it requires energy, right? So that is how we get our 36 ATPs per glucose molecule in aerobic respiration.